All right, today we're going to talk about Avogadro's number and the number of moles. Now, when you're working with amounts in chemistry, remember we have little tiny, tiny atoms or small, small, small amounts. But like I had anything to do with it. Chemists came up with a way of converting it to ways we can actually measure out and ways we can use. And those are moles. So in chemistry, a mole is amount of substance and it's based on carbon 12. Um, if you want 1 mole of any substance, all you have to do is measure out the mass from the periodic table. So if I want 1 mole of carbon, I'd measure out 12 grams. If I want 1 mole of calcium, I'd weigh out 40 grams. So that's what 1 mole is. Whatever the mass is on the periodic table, if you have that amount of that element, you have 1 mole. Now, if it's a compound, it's the same deal. Like for instance, the formula mass of calcium chloride is 111 grams. So if I measure out 111 grams of calcium chloride, I have 1 mole. All right. Now, Avogadro's number is the number of atoms. And we'll talk about that. The number of atoms that you'll find in 1 mole. So, for instance, water's formula mass is 18. Okay, if I have 18 grams of water and I measure out 18 grams, I have 1 mole of water. If I had no life, and I counted all the molecules in that 18 grams, I would find what they call Avogadro's number. And it's 6.02 times 10 to the 23rd. It's a huge number. It's 6 and then add 20, or 6.02, and then after that add 21 zeros. Okay? It was calculated mathematically. Nobody counted. Because you know what? If you started counting right now, you would not get to that number before you died. And you know, right in the middle of it, when you're like a 35 billion, somebody's going to interrupt you and then you're going to have to start over again. But Avogadro's number is the number of atoms in 1 mole, and it was mathematically calculated. And I'm going to show you how to work with those numbers to do conversions. So that we're going to do like we did before when we talked about dimensional analysis, converting from one unit to another. That's what we're going to do today. Okay, so Avogadro's number, again, we can't count molecules. They're too tiny. We don't have microscopes that would, you know, magnify them enough so we could actually see them. So like I said, it's been mathematically. So if we're talking about water, okay, each hydrogen is 1 and oxygen 16. So the formula mass of water is 18. So if I measure out 18 grams of water, this is 1 mole. And like I said, if you counted all the molecules in there, it would equal Avogadro's number. That's the number of molecules in 1 mole of any substance. It's not just water, any substance. If you have 1 mole of it, you have Avogadro's number of atoms. And Avogadro's number of atoms is 6.02 times 10 to the 23rd. So after your 602, you add 21 zeros. It's a huge number. It's like 6 hexillion or something. I'm not sure. Anyway, that's how many molecules are in this 1 mole. And again, it was mathematically calculated by a guy by the name of Amadeus Avogadro. How about that name, huh? Anyway, he's the one that figured out how many particles are in 1 mole of any substance. And it's called Avogadro's number after his last name. Okay, so again, 1 mole of carbon 12 has a mass of 12 grams. It has 6.02 times 10 to the 23rd atoms. They're all conversion factors. They all equal each other. Okay, and that's what this talks about too. So if I'm trying to get rid of moles and find particles, or it could be atoms, or it could be molecules, because again, if we're talking about a compound, it's going to be molecules, I would use these conversions. Okay, so by definition, molar mass is the mass of 1 mole of any substance. And that's what we've been figuring out when well, you can use the app on your phone to do that right now. But the molar mass of an element is the mass of all the elements involved multiplied by its subscript. Okay, the only difference between molar mass and formula mass is molar mass is for a molecular compound, 2 nonmetals, or 3 nonmetals, or whatever. And formula mass is between an ionic compound, a mass, and a metal and a nonmetal. But otherwise, you solve them the same way. Okay, so when we talk about moles of particles, again, if you have 1 mole, you have that many particles. And if we're talking about particles, it could be atoms, it could be molecules. So if you're talking about carbon, carbon is an element, its smallest particles are atoms, so it would equal atoms. If you're talking about a molecular compound, one that has molecules, notice the number's the same. Okay, And you can also even have it for ions, okay? We're just going to do for atoms and molecules. We're not going to do for ions, but you get the idea, right? Number's the same, okay? So, moles. Moles of an element is, again, 1 mole is a unit for measuring, and 1 mole of any element is the mass from the periodic table. Okay, if I have 1 mole of magnesium, it has 6.02 times 10 to the 23rd atoms. And again, it doesn't matter what your element is. If you have 1 mole, you have that many atoms. It never changes. Okay, so you can see it goes over and over. Moles of compounds, same thing. Okay, instead of atoms now, if it's a compound, I have molecules, but otherwise the number's the same. So it doesn't really matter. Atoms, molecules, works the same. Okay. Okay, so let's solve a problem. How many atoms are there in 0.551 grams of potassium? Okay, I know atoms in moles. I don't know in grams. So the first thing I'm going to have to do is I'm going to have to change grams to moles. So I know 1 mole of potassium, 39.1 grams. That comes from the periodic table. And again, if you just want to use 39, don't worry about it, you guys. It's fine. Okay. I know that 1 mole of any element, doesn't matter, but potassium has Avogadro's number. And again, we just use 6.02. Okay, the official one goes on a little ways, but 6.02 is fine. Okay, so I take my grams of calcium. I got to change it to moles. So what I'm going to do is I'm going to multiply 1 mole on top, 39.1 grams. And again, if you want to use 39, that's fine. But what's going to happen is grams of potassium are going to cancel out, and I'm going to have moles. Okay, so that's my first step. Get rid of grams and find moles. Now I have moles. I know how many moles, how many atoms are in 1 mole. So 1 mole, and then this is Avogadro's number. Again, so to solve this, what I'm going to do is I'm going to take 0.551, multiply by 6.02, and divide by 39.1. Then I'm going to take that number and I'm going to times 10 to the 23rd because this doesn't disappear. Okay? So you can see my grams cancel out, my moles cancel out, and what do I have left over is atoms. The question says how many atoms? Perfect. Okay? So again, what'll happen is when I divide this, or when I figure it out, I get 0.0849. Remember, we can't leave them like that. We have to write them in proper scientific notation. So that's why it was 0.0849 times 10 to the 23rd, and then I move the decimal over 2 to make it in proper scientific notation. So instead of 23rd, it's 21. You have to write your answer in proper scientific notation. Okay? All right. So again, remember grams, moles, formula units, or number of atoms, molecules, they're all based on each other, and it's just a conversion factor. Like 1 foot is 12 inches. Same deal. Okay? So it's just converting from one form to the other. All right, this one is hard to read, and I'm sorry about that. Okay, but the thing to remember is 1 mole of atoms, ions, molecules, whatever, is Avogadro's number. I think that's what they have up here to show you. Okay, like nitrogen's mass is 14. That's what 1 mole weighs, and it has Avogadro's number. Silver is, we'll use 108, Avogadro's number. It doesn't change. Okay, so Avogadro's number, 1 mole of any substance, 1 mole of you has Avogadro's number of atoms. Okay, so it doesn't matter if it's atoms or molecules or ions. 6.02 times 10 to the 23rd. That's the magic number. Okay. All right. Calculate the number of moles in glucose. All right. So I take my moles. It says I have 5.38 grams of glucose. So what I'm going to do is, because I have grams here, I want grams here. 1 mole glucose, if I take 6 carbon, 12 hydrogen, and 6 oxygen, add them together, I get 180. So this is the mass. And again, this is the number you can get from using that app on your phone. So all I'm going to do is this divided by this, and I get this. So 5.38 grams of C6H12O6 is 0.0, I would say 0.03 if you want to round, moles. Okay, so I'm just converting from one unit to another. Here's another one. How many moles of sodium bicarbonate, which is NaHCO3, in 580 grams? So, or 508, not 580. dyslexic today. Okay, so this is the opposite of this. This we started with moles, or we started with grams. Sorry, and we put grams on the bottom. Yes, so this is the same. Okay, so now what I'm going to do, again, 508. 1 mole has 84 grams. The 84 is 1 sodium, 1 hydrogen, 1 carbon, and 3 oxygen added together. I get 84. When I divide those, I get 6.05. That's how many moles there. If I started with moles and I wanted to find grams, I'd put moles on top, 1 mole and its mass on top. So it would be just the opposite. Okay? But they're just conversion factors. Okay, how many grams in 4.7 moles of calcium chloride? Okay, so now I'm going to start with moles. Moles, calcium chloride. Okay, calcium chloride has a mass of 111 grams. And I'm sorry I didn't put in all the units, but if I put in all the units, then it doesn't fit on one line and then it gets messy. So you'll have to forgive me. But 1 mole of calcium chloride is 111 grams, and that's 1 calcium and 2 chlorine added together. So I'm just going to multiply. 521.7 grams. So how many grams in 4.7 moles of calcium chloride? 521.7. And again, all I did was multiply this time. Okay. The way you set it up is, what do you start with? Whatever you start with, put it on the bottom. Okay. And again, this is just like multiplying by 1. Okay. The 111 grams is the formula mass of calcium chloride. And again, I put down, if you can use your app to find it if you've downloaded it. That's where it comes from. It's just 1 calcium, 2 chlorine added together. Okay. How many atoms in 2.4 moles of lithium hydroxide? Okay. So I put my moles. And again, I know 1 mole of any substance, doesn't matter what it is, has Avogadro's number. So my moles are going to be opposite and cancel each other, and I'll have atoms. So I'm going to take this times this, and I get 14.48, and then I tack on my 10 to the 23rd. I can't make that disappear. So now, to be in proper scientific notation, what I'm going to do is I'm going to move this decimal over 1, okay? Because I made this number smaller, I make this number larger. So make sure you write in proper scientific notation. Okay, how about if you get grams? Now you got 2 steps, okay? First, you got to change grams to moles, and then you can change moles to atoms. So I take my 45 grams of Na2O. 1 mole has a mass of 78. That's the formula mass. Okay, that's 2 sodium and 1 oxygen. And then, so now I've gotten rid of grams and I got moles. Then I'm going to put 1 mole on the bottom and Avogadro's number of atoms on top. So to solve this, I'm going to take 45 times 6.02 divide by 78, and that's 3.47, and then tack on my 10 to the 23rd. This one's already in proper scientific notation, so I don't have to worry about it. Okay? So again, these conversions are just like multiplying by 1. 1 mole of any substance is whatever its mass is from the periodic table. If it's a compound, it's like we did before. Find the formula mass. Find out what the whole compound weighs by taking the individual elements and how much of each element you have. If you have to convert it to molecules or atoms, then what you need to do is use Avogadro's number. And here, like here, I've been writing atoms when they're compound. I really should write molecules, but here's the problem with that. When I write, like when you start abbreviating moles and molecules, you get kind of confused. So if you want to just use atoms when it's really molecules, that's okay. You know, it's going to help so you don't get as confused. This should be molecules, but it works. Okay, so something to think about when you're doing these problems. All right, and that's it for today. We're going to start on something different with stoichiometry, using all this information and putting it to use next. So if you have any questions, again, let me know, and we will I'll do my best to help explain it all. Good luck.